Hello guys, welcome to this video. In this video we will be continuing all our previous explorations about all the functions and developments that we did, and in this video we shall also find out more about the properties and all the different discoveries that we can make about this exact function and the distributions that we are studying. And meanwhile there would be a lot of solved problems as well, so just head forward to the video. We can start over from there.
Well, the first problem is something like this. We have a sum over all primes p. Okay, we have a sum over the primes p given by 1 by p square into a function phi of p. Now this function phi of p is defined something like this. The function phi of p is given as product over all q's which are primes less than p such that q square minus 1 upon q square. So this is phi p. Now you see, let's have a look at what this exactly means. If we had phi of 7, let's say, so this should have been q less than 7, q square minus 1 by q square. Now how many primes are there? 2, 3 and 5, right? So this should be this into 3 square minus 1 by 3 square excuse me, into 5 square minus 1 by 5 square. So this should be phi of 7. So this is alike, right? That's how it goes. Now it really seems as a complicated one, but then again multiplying with it with 1 over p square, then again doing it summing over all primes, this all seems very much complicated, right? But this indeed has a beautiful answer, and we'll get to that in a very short time. But in the meanwhile, I need to explain a lot of things. Well, let's see if we can do that. Okay, so I'm just raising the example. Now this thing I already have taught in my channel, that the product of the primes given by 1 minus 1 by p square whole inverse is equals to zeta of 2. Zeta of 2 refers to the Riemann zeta function at the argument 2, which indeed equals pi square by 6. Well, we all know the Riemann zeta function at the value 2 is basically the sum of the reciprocals of the squares of the natural numbers, right? And we happen to know it in this way only, but there are alternate forms, there are integral versions, there are probabilistic versions, and then there is this prime version. Okay, so this also equals pi square upon 6. Now how does this product equal, that I'll be showing at the end, but for now assume that this is true and I'll just give you the justification at the end of the video. Now what we need to do, since we are dealing with the primes less than p in this product 5p, we understand that let's say p1, p2 and pk are all the primes less than or equal to p. That means pk is p, and they're in ascending order. That is, we have 1 less than p1, that is it starts from 2 most probably, 2 less than equals to p1, less than p2, less than p3, and so on, less than pk, which is equals to p. So this is the product. Now what happens if you multiply them out? What happens if you multiply these things out? Because you know q square minus 1 upon q square is basically 1 minus 1 upon q square, right? So it becomes something like this, right? Multiplied by a 1 by pk square. Now if you carefully treat this kind of sums are very normal. This kind of sums often come with a general idea of the product, and the product is just a sum because it's a symmetric polynomial, right? So the sum is basically the answer of this product, this the entire thing, this only 1 by p square phi p, this is equal to a sum of the terms which are of the form like this in various forms. Okay, various alternating versions, because there will be only a single one left, and that one will be multiplying with 1 by pk square. So there will be no one, every term would be of the form this. right? In alternating versions, sum of all the terms, most specifically, it's just a version. We don't mean to say every term has like this, but it's just a version. Okay, now this should be our product. Now there's a very beautiful way of treating this, because we already now know. Let me erase this, write the sum in our actual notation. Since we already know that this our sum S is equals to sum of primes P, and some of the terms of the form like this, right? All of the terms like this, don't be confused with the primes P. We know what it means, right? We know what it means right now, because we are summing over every P, and where P1 P2 varies because they are less than P. So for every P it changes. So this indeed it's a sum itself. Now imagine the situation. What this means? This means that basically, if you were to multiply all the primes in this format, 1 by p1 square, 1 by 1 minus p2 square, right, and multiply everything out, then only you will get something like this entire thing. Because here every product will be of the form like this in an alternating manner, and secondly they will be summed over all the primes, right? But there will be this extra one, because here in the previous sum there was no one, but here there will be an extra one, all the ones multiplied to get one. So it will be entirely 1 minus that, right? So S should be 1 minus this product. So just imagine this product being expanded out. What it gives you, it gives 1 minus this entire thing, this p1 square, p2 square, each and every combination that you can think of, right? That's what we exactly have here. So this basically gives you 1 minus product over primes, 1 minus 1 by p square, which means 1 minus, now this is equals to inverse of zeta 2, which is 6 by pi square. Because we already stated if there was a minus 1 in the power, then only it would have been pi square by 6, right? Okay. So this is the exact answer. Now we come to the part where we show this is indeed the answer. So I can safely erase this and come to the last part of the discussion for this problem, which is how is the product of the primes related to the Riemann zeta function, right? Okay. So to prove, 1 minus 1 by p square whole inverse is equals to zeta 2 aka pi square by 6. Now if you can assume that the summation notation, that is the sum over the naturals in 1 by n square equals pi square by 6, we are well and good to go. But if you still refuse to do that, we can do that. Let's say we can prove this one too. That's all again an easy part, because we know sin x upon x is equals to, you know what, 1 minus x square by 1 square pi square into 1 minus x square by 2 square pi square, and all that. This is called the Hadamard factorization of the sin x upon x. This is also an easy thing to prove, and you can do it by calculating the zeros and using and studying on different patterns of the Hadamard factorization and stuff, right? Okay. Now in this one, we can safely write sin x is equals to x times the product, right? N square pi square. Now every term is an even term here, right? So if you multiply out the x squares, you need to find the coefficient of x square in this product. Then you only need to find whatever it gets multiplied with 1, because you get that, right? So in that way, coefficient of x square in this term comes out to be something like this, summation over n 1 by n square pi square, because that's the coefficient. But in this entire thing, summation coefficient of x square is not valid. coefficient of x cube comes out to be this because the x square gets multiplied with the x. So on the right hand side, the coefficient of x cube is this. So on the left hand side, if we expand it by the Taylor expansion, we know x minus x cube by 3 factorial, right? Is this. Dot, dot, dot. So the coefficient of x cube on both sides must match, isn't it? Because it's an identity. So minus 1 by 3 factorial must be equals to minus summation over n 1 upon n square pi square. Or in other words, if you take the pi square and cancel the minuses, you get summation n 1 over n square is equals to pi square by 6, because 3 factorial is 6, and that's how we prove the Riemann zeta function at the value 2. See, that was pretty easy to understand at least. Now we go to the next part where we prove that the product is equal to the Riemann zeta function at the value 2. See, we start with the summation. It's a very interesting manipulation, and so consider this value as, which is zeta 2, consider this value n. Now what we are going to do, we are going to remove the prime factors all at once. So multiply out by 2. Do one thing, multiply out by 2. 1 by 2 square, 1 by 4 square, and all the way up to infinity. You multiply out by 2 square on the both sides, n by 2 square. Now subtract this equation from this equation, and you get n into 1 minus 1 by 2 square. And when you subtract the equations, you only have factors, all the terms in which the denominators are not factors of 2, right? Because I've eliminated every possible factor of 2. So you get everything except for 2, right? Do the same again, multiply by 1 by 3 square. So you get 1 by 3 square, 1 by 9 square, and everything on the factor of 3. Now the factors of 2 are already eliminated, so you never get a mixture of 2 and 3. You only get factors of 3, where 2 is not present. Again you subtract from this. So now what will be taken common? So you will subtract from the equation which was this, is equal to factors of 3. So you subtract this and this. Now n into 1 minus 1 by 2 square is taken common, and you get n into 1 minus 1 by 2 square into 1 minus 1 by 3 square. And you get everything. Those are not factors of things, right? So 2 and 3 are eliminated. In this way, if we can eliminate all the prime factors, which is an indefinite process but is guaranteed to end, if we can assume so, the only factor that will be left on the right hand side is 1, and on the left everything that will come is of the form this. So n into product of primes 1 minus 1 by p square will be equals to 1. So if you take this on the right hand side, product of primes 1 by 1 minus 1 by p square will be equals to n, which indeed is pi square by 6. So this product to the power minus 1, or 1 upon the 1 minus 1 by p square, is equals to pi square by 6, which actually proves our claim.
Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.